Hey everyone, my name is Charlie Homerding. I have been taking this class all semester, even though I haven't seen you guys or interacted with you guys through a Zoom call. Before I get started, I just wanted to give a shout out to Dr. Kissel. Thank you for a really challenging and rewarding class. I'm a full-time high school teacher teaching chemistry and physics, so this has been, a lot to juggle, but it's also been really awesome at the same time. And thank you to everyone in class for the problem solving sessions because I watched them every single week and they were incredibly helpful with doing the assignments. So thank you to everyone. And I hope you enjoy my presentation. It will be on electron spin resonance spectroscopy. All right, so the image here is an electron spin resonance spectrometer up in the top there. That is, I will go through the basics of what is in the spectrometer, but before I jump into how the spectrometer works, I do want to talk about the basics of this type of spectroscopy. So this type of spectroscopy, ESR, goes by a few different names. One of them is electron magnetic resonance or electron paramagnetic resonance. Both of those, I think, are appropriate terms because we are talking about how electrons interact with a magnetic field. The image there is our basic understanding of electron spin. Since electrons are a charged moving particle, they will experience a magnetic field. And if a magnetic field is put upon them, they will also interact with that magnetic field. So basically in ESR, we get to see how electrons interact with a magnetic field. This type of spectroscopy specifically studies paramagnetic material because it has unpaired electrons. Those are going to be more easily detected by it, and that's the best type of material for this spectroscopy. It is similar to nuclear magnetic resonance in the way that electron spins are excited, but not the spins of the atomic nuclei. So NMR deals more with the atomic nuclei, whereas ESR is going to deal with the electron spins. However, the electron spins are affected by the atomic nuclei, and we will see a little bit of how that plays a role when looking at the spectra of ESR. This type of spectroscopy is going to be useful in studying metal complexes and organic radicals. Probably similar to a lot of the stuff we've talked about this semester, especially with how some metal complexes have the splitting of the d orbitals. So we see those electron transitions in those type of materials, and I'm sure that this type of spectroscopy would pick up on similar electron transitions. It's going to utilize frequencies in the microwave region. So our source of electromagnetic radiation will be microwaves. And it was first observed by a Soviet physicist in 1944. At the same time, a British physicist was also developing the same technology. So here's a quick visual of what the energy transition would look like. So we see the negative 1/2 spin and the positive 1/2 spin. The electron is going to jump between those two spins because of the microwave radiation that is shot at it. And the energy change between the two spins is what the ESR spectrometer is reading. So this energy change between the spins. That's why unpaired electrons are going to be excited under the magnetic field, and the excited electron will change direction and they will relax. And as I said already, the microwave absorption is what's being measured as a function of the magnetic field. And here is an equation that illustrates the energy change between the electrons. G is the proportionality factor, and I will talk a little bit about G later on because G is really going to be the way that we identify what the sample is. The energy change is not necessarily the best indication of what the sample is. And then the other variables there, UB for the Bohr magneton, BO for magnetic field, and MS for the electron spin quantum number. That equation correlates with the energy transition in the graph. Here are the basics of the parts of a spectrometer. I actually really wanted to try to find the simplest image. There were a lot of more complicated images that I think were maybe a little too complicated for this type of project. Basically, there's going to be a microwave unit, some sort of source of the electromagnetic radiation. There's going to be a magnet, and in this image here that I also had in the beginning, those two large disks are the electromagnet that is creating the magnetic field between the sample. The sample is going to be placed in between that field there. And then there's also the spectrometer or the whatever is being used to actually detect the microwave frequencies and the energy being absorbed or released from the electrons. Here's another example here. So this source would be coming from the source would be producing the microwave radiation, and it would go through a detector. And it's kind of important what these detectors are, the phase sensitive detector. I will explain it in a future slide that actually changes what the spectrum looks like, and it changes the math of how we, try to understand that spectrum. So it's important that this is included here. And here's just another image of those two large disks that are the electromagnet, and the sample cavity is in the middle there where we are putting our sample to be detected. So here I have two different graphs. In most absorption techniques, you're going to see a graph that's similar to this one here on the left, where whatever we are measuring on the x-axis, in this case for ESR, we're measuring the magnetic field, and you'll see absorption on the y-axis. And usually we see peaks like this. But for ESR, we really don't see peaks that are like that. We see peaks that are actually the first derivative of the absorption. And the reason for this is because of that phase-sensitive detector. So we have to keep this in mind when we're looking at the spectra, and we're going to have to interpret it a little bit differently than a traditional absorption spectra. And here's just a few more details about that. The ESR spectrum is obtained by holding the frequency of the microwave constant. So the frequency of the microwave stays the same the whole time. That's not what's changing. What's changing is the magnetic field. So we're seeing how the absorption changes depending on the strength of the magnetic field. Absorption is going to occur when the magnetic field tunes in to the two spin states. So here's just that same image of the two different spin states and the energy transition. When the magnetic field kind of taps into that, that's when we are going to see a peak of some sort. And as I said in the previous slide, the peak is really going to be the first derivative of the absorption and not the absorption itself. Once this is tapped into, this is called the field for resonance. Here is the equation again that I showed, and this fraction here is the fraction for the proportionality factor or the G factor. And I'll explain a little bit about why that's important. So the ESR spectra can be obtained at a variety of frequencies. The field for resonance, as I was explaining earlier, doesn't really provide a unique identification for compounds. It's really the proportionality factor that can be more useful. So when we look at the proportionality factor for just a free electron, it's going to be 2.00232. When we look at organic radicals, the proportionality factor is going to be similar in that range from 1.99 to 2.01. And then if we look at transition metal compounds, again, like things that we've looked at throughout this semester, it can vary from 1.4 to 3.0. So these large variations occur due to the spin-orbit coupling and zero field splitting. So looking at this proportionality factor, that's going to be more beneficial in determining the identity of some compounds. So let's talk a little bit about the effect of the nuclei on the ESR spectrum. As I said earlier, this is not like NMR where we're looking at changes in the atomic nuclei. However, a nucleus obviously has an effect on an electron, right? So we can see these effects in ESR spectra. The unpaired electrons are sensitive to local environments. The nuclei are not that far from the electrons, so they are going to have an effect on them. Nuclei can have a magnetic moment that produces a local magnetic field on that electron, and this magnetic field, the local magnetic field from the nuclei, can be detected by the ESR. This interaction is called a hyperfine interaction. So it's going to provide even more information about the sample. Like we can figure out the number and the identity of the nuclei. We can also figure out the distance that from an unpaired electron to the nuclei. So all of this is pretty valuable information when determining the identity of a sample. However, another equation needs to be used. So this equation down here, it's basically the same equation with an additional term that includes the hyperfine coupling constant. And this image here shows some electrons splitting from the different spin states and how a nuclei can affect the energy splitting of the electron spin states. So these three graphs here kind of show how the nuclei are going to affect the spectra of ESR. The first image here is that image of a first derivative of the absorption. But when we throw in the hyperfine coupling constant, when we throw in the effects of the atomic nuclei, we actually sort of see this repeating pattern here. And the distance between those two peaks is going to be our hyperfine coupling constant. And then if we jump to this last image here, this would be coupling due to a single vanadium nucleus, and this can result in the ESR spectrum right here. So this kind of becomes the basis for what the ESR spectra looks like. This kind of repeating peak going back and forth. Here are two other examples right here. We have the ESR of a benzene radical anion. So we see that it has a unique pattern here with the A constant as well as the different peaks. And so it's basically a combination of that first derivative absorption along with the repeating A pattern. And the next one here is an ESR spectrum of a pyrazine radical anion. This graph here, it kind of puts everything together. So this is an example of ESR spectrum in quartz, where we have a titanium center and there are two subcenters, titanium lithium and titanium hydrogen. So we kind of see these peaks right here, and they all have that similar style that we've kind of been seeing, where there is a first derivative of absorption along with some sort of repeated A coupling. And then the middle absorption line represents the overlap of the two subcenters. So this basically sums up my presentation on ESR spectroscopy. I would just to kind of sum it up a little bit, ESR spectroscopy utilizes the energy change in electron spins within a magnetic field, and also the effect of the atomic nuclei will play a role in the ESR spectra, which create very unique spectras that have a few different variables that you need to consider upon analyzing it. Thank you so much for listening. I hope you enjoyed this presentation. Again, thanks for a wonderful semester, and I hope everyone enjoys their winter break.